So, we have been discussing digital circuit testing, right. I have introduced the concept of test vectors, fault models, in particular the single stucket fault model and the bridge fault model. Right. And then I have explained to you what is fault simulation, and I have explained to you what is meant by the D notation, D bar. Okay. So, the tools that generate test vectors, they may be based on backtracking algorithms. Okay, backtracking. So, there is no polynomial time algorithm, backtracking algorithms are used. So, in the worst case they may take exponential time. Okay. So, for example, if there are n inputs, they may take 2 to the power n iterations. Okay. So, this becomes too time consuming for large values of n. Okay. So, I will give you a very brief idea of how these these algorithms sort of work. So, there is a famous algorithm called as D algorithm. Okay. I am not going to go into too much detail of this D algorithm or anything like that, but I will just give you a quick idea. So, let us say we have some circuit like this, and let us say we want to find a stuck at test for a stuck at 0 fault here. Sorry, stuck at 0. So, the algorithm, what it will do is it will say, look, you want to put a value 1 on this line, okay, and that will cause a D to appear on this line. So, you can think of this as a D appears on this line, a D appears on this line, and on the same line in the reverse direction a 1 appears. Okay. So, for forward propagation it is D, for backward propagation it is 1. See, we need to put a 1 on this wire, we need to adjust the values of inputs, we need to select A, B, C, D such that 1 appears on the line, let us say we call this as E1, this is E and this is E1 and this is E2. But the moment a 1 appears on that line E1, we think of it as a D. A D appears on E1 for the purpose of forward propagation, and for the purpose of backward propagation it is 0. What is backward propagation? What we mean is we have to adjust, we have to work backwards and see how to put a 1. To put a 1 on E, when we work backwards, we may be able to say, hey, why don't you try 0 and x on this? That will work. Or we can try 0 and x, both of these will work. Now we have to, so we can justify E1 equal to 1 by putting BC equal to either x0 or 0x. Now that we are not done, right, we are only partially done. We were able to activate the fault, but we have to propagate the fault. In order to propagate the fault, we need to make sure that we have to put a 0 here, right, because if I put a 1 here, this will become 0. It will not propagate the fault further. Whereas if I put a 0 here, then 0 nor D will be D bar. So, the fault has moved forward. And in order to propagate this further, I need a 0, which I can do by putting, see, this 1 has already come here and this 1 is sitting here. So, the only choice I have is to put 0 here. Okay. So, the test is A equal to 0. I need A equal to 0 so that I can propagate this fault to the output. Oh, I am sorry, this I have made a mistake now. I have to put a 1 here because it is a AND gate. So, if I have an AND gate, if I have D bar on 1, the other has to be 1. So, that D bar comes at the output, and in order to put a 1, luckily I already have a 1 here. So, I need to put a 1 here. So, A equal to 0 will propagate the fault to this place. Let us say we call this F, propagates fault to F, and then suppose I call this G, G equal to 1 required to propagate fault to output. And in order to make G equal to 1, we can work backwards and say D must be equal to 1. So, the answer is A equal to 0 and x 0 1 or 0 0 x 1. They are all test vectors. So, there are several test vectors. So, 0 0 0 1 will work, or 0 1 0 1 will work, or 0 0 1 1 will work. There are 3 vectors that will work. Okay. So, I hope this point is clear. So, if I have a big circuit and let us say I am looking for a stuck at 1 fault here, this may be the output of some gate. So, the D algorithm assumes that I can place the value 0 here. Okay. because if I want to activate this fault, I have to place a 0, and that places a D bar on this side. So, I have to propagate a 0 backwards and a D forward. So, this is called backward propagation, it is called forward propagation. Now, how do I get a 0 on this line? D algorithm looks at what kind of gate you have. If it is an AND gate, well, you can get a D at 0 at the output of an AND gate by putting one of the inputs to be 0. Okay. So, suppose that is the case, suppose this is an AND gate. So, it says, well, I can put a 0x. This itself may be coming from some other gate. Okay. Because you chose this 0, you also have to worry about propagating that further. This may be going somewhere else and you have to simulate all that. So, let us say we have this is coming from an OR gate. D algorithm will say, hey, in order to get this 0, I need to put 0 0. And then once we put this 0 0, we have to simulate what is the effect of putting those zeros. When we are doing all this, it is possible that a conflict will arise. We think that we can do this 0 0, but that 0 0 may cause that the stuck at 0 line that we had assumed, it may not be able to put a D bar. So, the D algorithm will say, sorry, that is not going to work. I had tried 0x, now let me try x 0. Okay. And if both of them fail, then it will say that it looks like there is no test vector for this. Okay. So, D algorithm will want to propagate a D forward or D bar forward and a 1 or a 0 backward. So, if it manages to get a D or a D bar at one of the outputs, right, and if the inputs have been selected such that we can activate the fault, then the D algorithm concludes and says, I have found a test vector. Okay. The problem with the D algorithm is it sets all the intermediate lines to whatever it wants. See, it will assume that I can set this to 0 and it will try to justify, but it may not be possible to set it to 0. We may have to set the other line to 0. Okay. So, D algorithm assumes that intermediate lines can be set to 0 or 1 and then tries to justify. Okay. So, in the process it may end up doing some iterations. It may realize at some stage that was not possible at all. I could not have set that to 0 or 1 and it will go back and repeat. So, there is an alternate algorithm called PODEM. what that does is, it is very similar. If you want to stuck at 0 fault, if you want to try, you want to generate a test vector, it will again try to justify a 1 and propagate a d. But in justifying a 1, it will not assume that I can make this into a 1 or a 0, etc. It will go all the way to one of the primary inputs. And it will only, the PODEM algorithm will only modify the primary inputs. It will not assume that intermediate lines can be set to 0 or 1. So, let me show you a good source of this. So, here is a circuit, and our interest is in detecting a stuck at 0 fault on B, right. So, the D algorithm will assume that I can sensitize the fault by setting this to a D, which means I have to set B to 1. So, B is 1 and that will place a D on this line. Now, the D will propagate in both directions. So, the D will also go here, the D will also go here, right. Now, how do I propagate this further? So, let us try the top method. So, we will try to propagate it along this path. So, for that I have to place a 1 here. If I put a 0 here, this will become 0, the fault will not propagate to the output. So, I will put a 1, right, that will put a D here, and in order to propagate this further, we need to put a 0. So, D algorithm will put a 0 here, and then it will say, hey, how do I put a 0? So, that will require a 1 here, and how do I put a 1 here? Unfortunately, I can't, right, I can't put a 1 because C is the only thing I can control. There is a D here, right, I can't place any value here which will cause a 1 here. So, this fails. So, that is what I meant by saying the D algorithm arbitrarily assumes that I can do this. When trying to propagate the fault along this path, it assumed that I can put a 1. Well, in this example, A is a primary input, so it is actually able to put a 1, no problem. Then when propagating the D, it assumes that I can put a 0 here. Then when it tries to justify that 0, it says, hey, this has to be a 1, and then it looks at the previous inputs and it says, hey, I have a D here. So, it then realizes I can't do this. So, it will reverse. What was the alternate path? I could have propagated the D along this wire. So, this time it will put a 1 here, and that will cause a D to come here and a D bar to come here, right. And it may want to put a 0 here to propagate this further. So, a 0 will appear here, which I can do by putting a 0 here, right. So, a D bar will come here and that can be propagated further by putting E equal to 1. An alternate will be, we have already created A equal to 1. So, D is already here, right. So, D and D bar unfortunately will give a 1 and it will fail. The final method is what I just described. So, the D I am trying to propagate via this path. So, put a C so that the D comes here and becomes a D bar, put a 0 here so that I can propagate the d bar here and put a 1 here so that the d bar. So, this is a test vector 0 1 1 1 is a test vector. Okay. So, here is an example. Okay. So, here is a test vector and we want to detect a stuck at 0 fault here, and we try to do that by putting a 1 here. So, putting a 1 on A will activate the fault and it will cause a D to appear on this line, and that D will go and be available in both these places. So, that means I can propagate it through this path or I can propagate it through this path. Okay. Now, D algorithm will select to do one of them. Okay, let us say it decided to do it using the first one. Okay. No, I think they have chosen to do it this way. Okay. So, D has come here. To propagate it to this wire, we can put a 0 here. See, this is what D algorithm does. It assumes that I can put a 0 here. And in order to put a 0 here, I need 2 zeros here. And in order to get a 0 here, C can be 0 and B can be 0. So, B and C can be made 0. So, that will put a 0 here. And if I put a 0 here, this will become a 1, and that 1 will cause a 1 to come here, and 1 and D will give me a D bar. So, in this example it worked out. Okay. So, it was luck. Okay. We have placed a 0 here and activated the fault, and in order to activate the 0 here, we need a 1 here, and the fault gets activated and puts a D bar. The D bar travels here as well as here. Okay. And we have a choice on how to propagate it. Meanwhile, this 1 has to be justified. Okay. So, the 1 is being justified. Okay. So, if I decide to propagate it along this path, I need a 0 here, which means I need a 1 here. Okay. And if I have a 1 here and I want a 1 here, then I should have a 1 here also. Okay. Only a 1 and a 1 will cause a 1 here. This is an XNOR gate. So, I need to have a 1 here, and that means I have to have a 1 here and a 1 here, and this 1 here will come here, and it will end up propagating that D as a D bar. Okay. That is what they are saying. Okay. We already got a D bar, and this D bar is sitting here. I do not think we need to propagate it in both the places. We are sort of done now. So, putting B equal to 1, see here is another example. We want to test for stuck at one fault here, which means I have to put a 0 on this line, right, and as a result it will get a D bar, right. Because we placed that 0 here, this automatically became a 0 and this has to be a 1. So, these are some decisions that have already been made for you. Now, to propagate this D bar along this gate, I need to put a, see here I have a choice, this is an XNOR gate. So, I can put either a 0 or a 1. Okay. See, if I put a 0 here, it will propagate a D. If I put a 1 here, it will propagate a D. Okay. So, they have assumed that we are going to put a 1. Okay. So, they have assumed that we will put a 1, and as a result 1 XNORed with D bar will be D bar. Okay. And we can to propagate this further, we need both of these guys to be 1. So, C is 1, that is not difficult, but this also has to be 1, and that 1 would mean 0 on this line, which is okay, right, and it became a D. Okay. And just a minute, we had a 1, that 1 came here, we have already assumed a 1 here. So, if this has to be a 1 and this has to be a 1 and we have an XNOR gate, we need a 1 here, and therefore, this has to be a 1, and this 1 will go here, 1 and 1 will result in a 1, and this 1 and this 1 will give us 0. Okay. So, it worked out. Okay. In this case, we are able to find a test vector. Okay. But there are situations where the D algorithm may fail to propagate D and at the same time justify the input so as to activate the fault. Okay. It may try many times, right. So, someone came up with an alternate algorithm, somebody called Prabhu Goyal. Okay. So, Prabhu Goyal is given the credit for the PODEM algorithm. The D algorithm was invented by trying to remember his name, very well known person. I do not know whether his name is mentioned here. Yeah, his name is Roth. Okay. Roth was from IBM, and in 1966 he invented the D algorithm. Okay. Whereas I think Prabhu Goyal invented it little later. He was, I think, at AT&T Bell Labs when he invented the D PODEM algorithm. Okay. So, PODEM stands for path oriented decision making. Okay. So, here is how it differs. Okay. Let us say we have to find a stuck at one test for a stuck at one fault here. Okay. So, this means we have to put a 0 on this line, which means I have to put a 1 on this line, right. So, in D algorithm he will put that 1. So, Roth assumes that I can put this 1 and then try to justify. But PODEM, what it will do is it will take a path from this point to one of the primary inputs. So, it will try as a path. Let us say I go like this and go like this and go like this and go like this and go like this. So, I can reach from here to A and it will count the number of bubbles on the way. See, there is one bubble here, 2 bubbles, then 3 bubbles, and I have come to A. So, between A and this point there are 3 bubbles. So, if I want to put a 1 here, 0 here, then I should put a 1 here. So, that is his logic. Okay. By putting a 1 here, it is likely to place a 0. It may not place. Okay. If I put a 1 here, I am still not done, it's still nothing is decided. Is that okay? Then he will say, hey, did I get that 0 that I want? Not yet, because by putting a 1 here, I have not yet been able to get a 0 here. So, it will again try another path. So, it may go like this and go like this and go like this and come to this. How many bubbles are on the way? 0, there is 1 bubble here, 2 bubbles here, 3 bubbles here. Again he will say maybe if I put a 1 here, it gets a 0. Now that both of these are 1, immediately I will get a 1 here, and this 1 will come here, and this 1 will go here. Okay. But the thing is 1 and 1 will result in a 1 here, right, and this 1 and this 1 will result in a 1 here and a 0 here. So, in 2 iterations I am able to activate the fault to 0. I am very confident that by placing a 1 1 here I am able to place a 0. That means I can get the D bar to come here. Now, in order to propagate this further, see, luckily I already have a 1 here, okay, and that has resulted in a 0 already. So, it has already propagated to y. So, the algorithm is done. I hope you understood the idea behind PODEM. PODEM says I want a D on this line, I am sorry, a D bar on this line. So, I need a 0. So, how to get a 0? So, it will trace a path from this point to one of the primary inputs, and if it wants a 0 and if the number of bubbles on the way is odd, then it will put a 1. If the number of bubbles on the way is even, it will put a 0. In this example, from here I see 1 bubble, 2 bubbles, 3 bubbles. So, it says hey, A must be 1, that is likely to cause a 0 here. So, it puts A equal to 1, but that does not do much. Okay. By putting A equal to 1, we are not really able to put a 0. So, it tries again a different path. So, this time it may choose this path, again 3 bubbles on the way. So, it will again put a 1. Now, both of them are 1. So, 1 and 1 will give me a 1, and this 1 and this one comes here, and this is already a 1. 1 and 1 will give me a 1 here, and that one gives me a 0. Okay. So, I managed to get a 0 that I was looking for, and because this is 1, this becomes 0, and 0 ORed with D bar will give me a D bar. Okay. So, no, it will not struggle with conflicts unlike the D algorithm. So, that is the advantage of the PODEM algorithm.